law of partial pressures is not a fundamental law of gases. It is sort of a application of pressure, and we need to think about, so first of all, what is partial pressure, and then introduce the law of partial pressures, and then talk about how it's useful. So the idea is that partial pressure is simply just a trick. It's a mathematical trick for assigning individual pressures to different components of a mixture. So if I had a mixture of, say, water and carbon dioxide, those are both gases. I've had the steam and carbon dioxide. Then I have a total pressure of the whole gas mixture, but I want to say, yeah, but how much of that pressure is from the water pressure and how much is it from the carbon dioxide pressure? And so partial pressures kind of allow me to assign it. So again, the more particles there are of a given type, the more responsible they are for the collisions. So it's really kind of separating out my mixture by, well, how much water do I have and how much carbon dioxide do I have? And I can kind of say, well, then I imagine the pressure is going to be, contributions are going to be proportional to what percentage of the mixture is that component. Okay, so writing the equation can be a little bit funny because it depends on what your mixture is. The statement is that the total pressure of a gas mixture is equal to the sum of all the partial pressures of the mixture components. Now, breaking that down into a math equation is a little bit tricky. So if I have a gas mixture that contains three components, gas A, gas B, gas C, then the total pressure is equal to the partial pressure of gas A plus the partial pressure of gas B plus the partial pressure of gas C. And again, that formula depends on, well, how many components do I have? So often it's written as P total is equal to P1 plus P2 plus dot, 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 meaning keep going until you have all of the number of components. So if I only had two components, it would be the partial pressure of the first one and the partial pressure of the second one. Notice that whether I call it a pressure or a partial pressure depends on this subscript. If the subscript is describing one component, it's a partial pressure. If it's not, if it's describing the whole sample, it's the total pressure. So it can be a little bit difficult picking up from context if something's a partial pressure or a total pressure. So this might be an example. So it's a great practice skill. It's all I need you to do is come up with a specific equation for Dalton's law for air, and air has all these different components in it, and another one for what would be the specific Dalton's law equation for a mixture of carbon dioxide gases collected over water. Remember, if it's collected over water, some of that water will evaporate, so I can imagine that I'm going to have some water vapor in that mixture of spaces. So come up with those and we'll discuss them when we get to class. Continuing on, let's talk about how would you go about measuring partial pressure. Well, the answer is you can't. Remember, the pressure is sort of the force that those particles hit, the force that is applied to the walls as they hit the walls. Well, there's no way we can measure which particular particle it's coming from. The particles are incredibly tiny, and the sensors only feel the total effect. So we can measure the total pressure, but we really can't measure a partial pressure of did that pressure come from a red molecule or a blue molecule or a gas water molecule or a carbon dioxide molecule? But we do know that the total number of collisions, since they all collide at the same rate, will be proportional to how much within the total is that mixture component. So the way we will write this is that the partial pressure of gas A is equal to, this is called the mole fraction of gas A times the total pressure. Essentially, this is like a fraction, a ratio of how many of the particles are A particles out of the whole total multiplied by the total. So it's really kind of I'm just ratioing up the total pressure into, well, it's this much from A and this much from B based on how many molecules there are of each. Remember that moles is a set of molecules. So really, when I'm measuring the moles over the total moles, I'm really measuring how many molecules of A are there compared to the total number of molecules in the mixture. So in order to calculate the mole fraction, I would need to know how many moles of A gas A are there compared to the total number of moles in the mixture. And this is kind of a ratio or a percentage, only it's not in basis of 100, of how much of the mixture is particles of A. And then I multiply that by the total pressure and I can get the partial pressure. Sometimes I can do different tricks and experimentally we can do some pretty tricky stuff and measure the partial pressure. Not really, we're measuring it indirectly, and then use it to figure out the mole fraction of what's in a gas mixture, and that can be kind of powerful. So a lot of times where this gets applied is when we're collecting gases over water. Gases are tricky things to work with experimentally. You know, you have to contain them because they don't like to be contained. So sometimes the way we collect things is we need to sort of seal off. We need to allow the gases to move, but I also kind of need it sealed off. So a lot of times we'll use water. So we can bubble a gas through water so the gases are free to move through the liquid water, but the water kind of seals it off so it can't completely escape. And when we do that, the problem with it is that water itself can easily evaporate and form water vapor, which is water in the gas form. So if I have gases of water, it mixes with the gas that I'm interested in, and I'm actually collecting two gases at the same time, and I need to be able to correct for the portion of the gas that is really water versus the portion of the gas that I was actually trying to measure. So note that when this happens, whatever gas I'm collecting is the gas that I'm interested in, but I will also have some water pressure there. I'm going to have some partial pressure due to water vapor. So the total pressure which I can measure is equal to the gas I'm interested in's partial pressure plus the partial pressure of water. It turns out that experimentally we've developed reference tables of what the partial pressure of water is. There's some experimental tricks we can do to get what the water pressure should be at different temperatures based on evaporation rates. And from that, if I can measure the total pressure, but I'm really interested in, well, what was the pressure of just the gas that I was interested in, I can subtract off the water vapor pressure and I can get the gas pressure that I'm interested in. So this is what a water vapor pressure table will look like. Note that it has different temperatures. The amount that will evaporate, the pressure, partial pressure of water in the water vapor in the space, is going to really depend on temperature. As the temperature goes up, so does the amount of vapor pressure. Note that 100 is the boiling point of water. I'm going to have a lot of water vapor there. I'm going to have a full atmosphere worth of water vapor there. But at normal room temperatures, it's fairly low. These are in millimeters of mercury. So we'll practice this one in class as well. What is the pressure of CO2 collected over water in a lab at 777.8 millimeters of mercury and 23 degrees Celsius? So we will work on that in class. A similar one, a liter container has 0.642 atmospheres of nitrogen and 0.116 atmospheres of argon at 22 degrees Celsius. If 0.1 moles of oxygen are added to it, what is the total pressure of the gas mixture? So here I'm going to have to do a little bit trickier ways to get to the total gas pressure, but try it on your own.